Okay, very good afternoon. Thank you, Professor, for the wonderful lecture on photolithography. In continuation with your lecture, I am going to give one basic idea about the details material characterization, which will be helpful for the materials laboratory. We will be discussing some basics of that characterization techniques. Okay, so I welcome you all for this section. We'll go for the introductions. So here, one material characterization is the process of understanding the structure, composition, and the properties of the material. If you are not understanding this character structure, then very difficult to find out the chemical composition. The structure and the chemical composition will decide the properties of the material. So, it material characterization is bridge the gap between processing, structure, property, performance. This line diagram is the heart of the material scientist in their mind. They have to do the processing. Processing will decide the structure in the sense microstructure, then it will leads to the mechanical property. Then based on the properties of the material, the performance is going to be live. So the level of characterization, if you take out, there are three level of characterizations are there. First one is macro scale. Macro scale in the sense visual examination. Once you have done, you have to physically you need to judge whether it is done or not. Then followed by that hardness testing you can do. Then micro scale in the sense optical microscopy, then scanning electron microscopy. Then coming to the in-depth level, that is called nanoscale. There it will be going to TEM and AFM, then X-ray diffraction, then some spectroscopy. The application of the material laboratory. Without material laboratory, the engineers will struck in between somewhere. Okay. So what is the application of the material laboratory? It will come under the quality control and failure analysis. If you want to improve the quality and if any failure happen, if you want to know the root cause of the failure, that study is called failure analysis. They will take out the sample from the failed spot, then from the reverse engineering, from the back they will study why it's caught, why that catastrophic mode of failure happened. So that is called failure analysis study. To improve the quality control, we need the materials lab, and to develop the alloy, composite, ceramic, polymer. These four are the engineering material. So to develop such kind of material, you require the materials lab, and for surface engineering and coating analysis. Surface engineering means to modify the surface in order to improve the performance. And also coating, just a few minutes back, the professor was discussing about the coating, the advanced end, that is called lithography techniques, he has explained. And also, from the slide, we conclude that the characterization is the backbone of the material science, and it is guiding us to design the next generation of functional material. So coming to this classification, there are three ways we can classify: structural characterization, then chemical characterization, then mechanical characterization. We will be going to see the five different kind of study. In that, this all the characterization will be implemented there. How the execution of that project. So in the structural characterization means we can done by the X-ray diffraction study, which will be helpful to identify the crystal structure and the phase identification. Lattice parameter. Lattice parameter means the length of the unit cell. That is called lattice parameter, like ABC. So that one, yesterday lecture, professor was explaining in a nice way, like Previous lattice he was discussing. Then coming to the SEM nothing but scanning electron microscopy to study the surface topography, then microstructure, element analysis, then followed by TEM, FEM, all those things. Coming to the chemical characterization, EDS, XPS, and AES, this all find out the chemical composition of the material. Coming to the mechanical characterization, hardness. This is a hardness can be done by Brunel, Rockwell, Wiggards, and nano indentation. Then coming to the tensile and the compression test, which can be done with the tensile testing machine. From there, we will get the data of yield strength, ductility, the mode of fracture, so on so. Then impact test used to find out the ductility of the specimen. especially toughness, the amount of energy absorbed during the fracture, we can able to measure. So coming to the creep and fatigue, these are the high temperature performance testing, which are also available. So this is the one study, that is a diffusion bonding of commercially pure titanium to 304L stainless steel. Little bit brief I will give you about the history of the specimen fabrication. This bonding of titanium to stainless steel is highly challenging because there is a limited solid solubility in iron and titanium. Because of that, while doing the fusion based welding process, like where melting and solidification taking, that time there is a evolution of intermetallic compound called FeTi, Fe2Ti, like that kind of intermetallic compound will evolve. That compound is called brittle intermetallic compound. So immediate fracture you can find out. If you done, if you want to join these two material with the fusion based welding process, such as shielded metal arc welding or TIG welding or electron beam welding or laser beam welding, that kind of mode, immediate fracture you will notice because of the formation of this brittle intermetallic compound. So the solution behind that one is you have to change the welding technique. That one in your hand, the solid state welding techniques are available. In that diffusion bonding, you have chosen to join these two material. What is the reason behind to join these two material? These two materials are highly used in nuclear power plant where the spent fuel reprocessing plant units are there. Spent fuel means irradiated nuclear fuel, like uranium 235. Already one bombardment over, the balance fuel is called irradiated fuel. That fuel we need to handle it. The problem in the nuclear power plant is handling the waste, nuclear waste. It will always emit radiation. So the one of the techniques called spent fuel reprocessing plant. That means whatever already we have done the bombardment over, the balance fuel is called irradiated fuel. That fuel they will cut it into small pieces and they will put it in the dissolver tank. That tank is made up of the titanium because that solution is called concentric nitric acid. That nitric acid is highly corrosive fluid. So in order to store that nitric acid, the tank is made up of the titanium because titanium having high corrosion resistance in it. Okay. Then balance components made up of the stainless steel. Stainless steel we know 304 is a austenitic stainless steel. L indicates low carbon in it to avoid the sensitization behavior. Okay. So here we have joined this two material with three different bonding temperature. Here it is 850 degrees Celsius, 900, 950. So the diffusion bonding means when the temperature will give the interdiffusion. The temperature is the activation energy for the interdiffusion. Element from A to B, B to A, like that interdiffusion will happen, the bond will come. That is called diffusion bonding. Diffusion phenomena is the major role to join that one. So here, since temperature assisted process, we are not knowing what temperature it will be good. So we are changing the temperature from 800, 850, 900, 950. You can see this is a cross-sectional view of the bonded surfaces. Is clear the joints are intact, but there is some evolution of some layer by layer something is here. So we are keen to study that one. So this is from the SEM characterization, that is SEM, scanning electron microscopy, that there are some electron particle interaction will come. In that secondary electron signals they will collect for the SEM analysis. There are three more signals will come, like characteristic X-ray will come, backscattered electron will come, transmitted electron come. In the SEM is mainly focused on the collection of secondary electron. Secondary electron signal it will collect and it will frame an image like that. This is a cross-sectional view. You can see this is titanium side, this is steel side. So like same way, titanium, steel side. So with respect to bonding temperature, you can clearly notice that this is the interface layer. The interface size is getting increasing with respect to increasing temperature. That means while increasing temperature, the diffusion kinetics getting increased. Because of that, the interface layer is getting increased. So now our idea is whether is there any intermetallic compound formed or not. So to study that one, we have taken the sample to the X-ray diffraction technique. This X-ray diffraction technique, already professor told, it is a Bragg's law, the principle of the X-ray diffraction is Bragg's law, n lambda equal to 2d sin theta. From there, the peaks will come here. So you can see there is a evolution of that Fe2Ta compound, Fe2Ta compound. Here also Fe2T compound. Irrespective of the bonding temperature, in all the three specimens, there is a evolution of Fe2Ta compound. That is a brittle intermetallic compound. So one information we noticed, even with the solid state welding process, there is an evolution of Fe2Ti. And other intermetallic compound like FeTi or some Xi phase is coming, Xi phase. That kind of phase is not able to detect in the X-ray diffraction. The reason behind that, there is a limitation in the X-ray diffraction technique. If the volume percentage is more than 5%, then only X-ray can detect the compound. So the possibility of the detection of that FeTi and other intermetallic compound, because their evolution may be lesser than 5%. That is why it may not be detected by the X-ray diffraction. So this is then we have zone wise we segregated. How it is possible? That is, this is called EDS analysis. EDS analysis nothing but energy dispersive spectroscopy. Across the joint interface, we can do the line scan analysis. That line scan done by that characteristic X-ray will be coming out from the electron is coming from the electron gun through thermionic emission. The second electrons are coming. That electrons will interact with the specimen. Then various signals will produce. That is called secondary electron, then backscattered electron, then characteristic X-ray. So through that X-ray, this kind of detection happening. This is the energy dispersive spectroscopy, the line scan. You can see that red color is nothing but titanium. This right side is stainless steel side. So stainless steel, that major principal elements such as iron, chromium, nickels are there. Here it's a pure titanium. Since it's commercially pure titanium, 99.99% titanium only, you can see that titanium elements are there. The indirect diffusion phenomena, you can easily understand by the energy dispersive spectroscopy. So initially, after bonding over, visual examination we have to done, then cut, we have to prepare the sample metallographically. For the indirect diffusion kinetics, we can studied by the EDS analysis. For visualization topography study, we can done by SEM. What are the phases was evolved? That one we can detect by X-ray diffraction, XRD, X-ray diffraction technique. And coming to the mechanical property study. So because of the evolution of intermetallic compound, is there any problem in the mechanical properties or not? That one, majorly we have focused hardness and the tensile test. This is a hardness profile. Clearly we can say this is a base material stainless steel side, this is titanium side. So along the mid thickness, we have measured the hardness. It is gradually increased. At the interface region, there is a hike in the hardness profile. You see, the base material showing hardness of 200, but that interface it is showing 400 VHN. This is a biggest micro hardness tester. That means why suddenly at the joint interface there is a steep increase in the hardness. The reason behind that, already we have seen at the interface there is a evolution of Fe2Ti. Okay, that is noticed. Then we go into the tensile property. Tensile property as per the ASTM E8, the round tensile specimen we have fabricated with the universal tension testing machine we have tested. Then we can see the mode of fracture. You see, it is the fracture is failed perpendicular to the joint interface perfectly without any significant deformation. It has failed. That indicates it's a brittle mode of failure. So why it's kind of brittle mode of failure happened? Because of the evolution of intermetallic compound. Irrespective of the bonding temperature, either it is 800, 850 or 900 or 950, everywhere the almost same failure mode is noticed. And we took that one to study what kind of features are there in the morphological pattern. We taken to the X-ray. Again, we have taken the scanning electron microscopy to study the failure analysis. So there, this is a fractograph. You can see this kind of pattern is called river pattern. This is called, there is absence of dimple structure. This is all called cleavage mode. This kind of pattern indicate it is it's a brittle mode of failure. So why brittle mode of failure happened? Because of the evolution of mm, intermetallic compound. Why intermetallic compound came? Because of the limited solid solubility between these two dissimilar matrix of titanium and iron. That is why it is came. But in the case of fusion welding process, immediate failure you can notice. There the chance is more. But with the solid state technique, we have minimized the evolution of FeTTI, that kind of intermetallic compound, such that therefore at least 5% of ductility we got something. Okay. So this is the next study. This is called the multipass friction stir processing of pure copper. That means we have taken the copper material. Already copper we know it is high thermal conductivity material. It's electrically it's having enormously people are using for the engineering application. But the problem behind the copper is we have to enhance the strength of the material. So what we have done, we have taken the copper, then we done some severe plastic deformation by the friction stir processing. So the short form is FSP. That friction stir processing is nothing but it's one of the solid state welding technique. That one we can be used as a the changing the surface morphology. Okay, surface engineering. We can take the same welding machine as a surface engineering material. So we have done some processing. Here you can see this is the base material of the copper. As we purchase from the market, this is a bigger grain size are there. But doing the first pass, once you do the stirring action, then the entire texture is changing. The grains are getting very finer. But if you do one more time on that same area, that is second pass, then again the grains are getting finer. If you do one more time, then it is more finer you are getting. That means from the coarse grain to fine grain we are getting through number of process you are doing. Why this kind of change is happening? Because the FSP associated with the severe plastic deformation, there's a new grains, recrystallization happening. The strain-free grains are coming through the dynamic recrystallization. That process is associated with friction stir processing. That is why by increasing the passes, the size of the grains are getting lower. So here you can see the base material, the grain size is approximately 5.57. But after doing first pass, the grain size is 0.69 micrometer. Then by second pass, 0.91. Little bit of grain coarsening happened because of the thermal cycle evolved. Then coming to the third pass, again it is going down. It is 0.62. So that way we are changing by doing the friction stir processing, we can change the morphology of this one. This is the pattern we have taken from the electron backscatter diffraction technique. That is called EBSD. There they will collect the signals of backscattered electron. As already we have discussed, the electron particle interaction, various signal will produce. Here with the detector will collect the backscattered electron. From there that kind of image is forming. Now we have taken the material to the XRD. So XRD again to study the phase identification. Then we are more keen to know by doing the severe plastic deformation, is there any new phase came or not? So to study that one, we have understand that there is no new phases evolved, but there is a significant peak shift we have noticed. You can see in the base material, the peak was, the 100% peak was 43.32. But after doing first pass, the peak was little shifted to 43.72. Compared to the base material one, by doing the friction stir processing, there is a peak shift towards the right side of the peak one. That means higher angle side, there is a peak shift is there. There is a thumb rule. There is one thumb rule is there. If peak shift towards the right side, then there is a tensile mode of residual stress will be there, because the lattice contraction happening due to the severe plastic deformation. If it is in left side, the peak is shifting towards the left side, then there's a compressive mode of residual stress might be evaluated. This is a thumb rule already. So we have noticed that irrespective of the number of passes, compared to the base material, all the three specimens, there is a peak shift. That too, it is towards the right side. Then coming to the hardness measurement, then we have taken the sample to the hardness measurement across the specimen. From the top to bottom, we have measured. You can see the base material one is a red color, black color one, almost steady profile of hardness variation. But by doing the number of passes, first pass, second pass, third pass, the hardness is getting increases. That means the third pass showing superior hardness than that of previous passes, second and third, then that base material. That means by doing the friction stir processing, the grains are getting disoriented. We are getting very strain free. Finer grains are getting, finer grains are giving the higher hardness according to the famous relation is called Hall-Petch relation. So that way we can relate here. You can see here processing, friction stir processing decide the microstructure. Microstructure is decided the properties. Properties decided the performance. It is well matching with our new characterization now. Okay. Now coming to the another topic. That one, as professor was explained, that is a macro level coating. That is, Sir has taught you in the lithography in micro scale coating. But here we have tried with some macro level coating. That is called zinc coating on the dual phase steel. Dual phase steel, the short form is called DP steel. Dual phase means there are two different structures will be there in the base matrix. Dual phase means one is martensitic structure, another one is ferritic structure will be there. Okay, so that is called dual phase steel. This steel is a high strength steel because it's a tensile strength is roughly 500 MPa, you can say. So that is enormously people are using in the engineering application. The problem behind the DP steel is it's a corrosion resistance. Since the chromium content is very less, it is try to form the oxide. Immediately the rusting will form. So in order to avoid that one, coating is required. Conventional coating techniques are there, but that kind of coating will deteriorate the substrate also. Substrate also it will affect. So our study, we have taken the zinc as the coating material. We have done through friction stir processing. Is there any possibilities there or not on the surface coating? It's a new trial we have done our laboratory. This is a friction stir welding machine. This is a zinc plate. Below that substrate material is DP steel. So we have done the friction stir processing. You can see the photograph of the macrograph of the coated one. So first characterization is visual examination only. We have to judge whether coating is done or not. So we have physically we have seen that's a uniform coating across the face plate. Then to study the coating thickness, we have cut the specimen. Metallographically we have polished, and this is a cross-sectional view of the photograph. You can see the top side, there is a zinc coated surface, and this is a base plate. Now again, with this surface, our aim is to, without deteriorating substrate, the how much effectiveness the coating can possible. So that way, during the processing, is there any parent material getting affected or not? So for that study, there are two locations we have taken. One is the location adjacent to the coating interface. Another one location is far away from the coating region. These two locations we have taken, and we have studied the microstructure. We have studied the properties. Is there any changes happening or not? This is in the optical microscope. This very basic one, optical microscopy. The image is showing that there is an insignificant difference between both the location. Then coming to the X-ray diffraction we have taken. This is a base material of DP steel. Zinc coated one also we have measured. Then there we found that there is a evolution of zinc peak is there. Zinc peak is there. In addition to that, the base plate also there. Base plate peak also came. That means the coating is not that much depth actually. So the surface coating, since we have taken only 1 mm thickness plate on the surface, some of the plate is deteriorated during the process. That is why the DP steel peak also came. You see the cross-sectional we have taken. This is the coated area. This is the base plate. Then hardness measurement we have taken. This is biggest hardness profile. From top to bottom we have taken. You see the indentation size itself indicate that there is a significant difference in the hardness variation across the coating surfaces. The bigger size, bigger indentation will indicate the lower hardness, because the biggest hardness formula is VHN is equal to P divided 1.854 P divided by D square. D square nothing but the size of the indenter. More and more size, the lesser will be the hardness, because it's inversely proportional. So you can see the zinc coated area, the hardness is roughly 75 VHN. Then gradually it is increased, the base material hardness we reached. Okay, that means there is no insignificant difference noticed at the adjacent area of the coated interface. That means with the friction stir processing, without any significant problem, we have done this successful coating on that DP steel. This is another work. This is the again dissimilar matrix of 9 chrome 1 mol is to 2.25 quarter steel. 2.25 chrome 1 molybdenum steel. This is called P91 steel. This is called P22 steel. These two steels are the structural material in the nuclear industry. So here the composition you can see 9 chrome means there is approximately 9% chromium will be there. The 2 quarter 2.25 means approximately 2.25 chromium will be there. So this one we have done this kind dissimilar material with the friction stir welding as well as TIG welding process. Initially the characterization start with the visual examination. You can see the visual photo. The after the welding there is no significant, there is no crack on that. Successful welding has been achieved. So in the welding we have taken the two different parameters. One is 200 rpm, then 500 rpm, to study the effect of rotational speed on the joint strength of the material. This is the photograph of the TIG welded one. Now comparison between the two end. One is fusion welding, another one is friction stir welding. Again the comparison between lower rpm, higher rpm. So this is a joint geometry of the friction stir welding. This is a joint geometry of the A-TIG welding. A-TIG welding nothing but activated TIG welding process. Because of the activated flux we have to use prior to the welding, that one reversal of the Marangoni effect. That's why depth of penetration will be more. So that is the A-TIG welding. Since it's a fusion based welding process, in order to protect the weld material from the atmospheric contamination, shielding gas you supposed to give, here I have used helium gas, because helium having higher ionization potential, that is 25.1 electron volt. So if you are using higher potential shielding gas, we can minimize the heat input. If you are minimizing the heat input, we can get the narrow heat affected zone. That is why the high end fusion welding process. That means we cannot go for the electron beam welding because of the cost factor. So out of that, A-TIG welding can be a high end one. That's why with the minimum heat input, because we are applying helium gas as a shielding effect. In the case of friction stir welding, since it is a solid state welding process, there is no melting and solidification, so there is no requirement of shielding gas. So it's a solid state itself, the welding can be possible. So coming to the, this is the base material of 9 chrome 1 mol steel. Okay, this is the base structure of the 2 quarter 1 mol steel. So here you can see, this is the lot of precipitates are there. This is a chromium carbide precipitates, M23C6. These are MX precipitate. These precipitates are the strengthener for the material. That is why these materials are used for the high temperature application. So this is the friction stir welding photograph. The cross-sectional photograph, we have to take on the, cut the specimen. Metallographically, we need to prepare the sample via the polishing technique from coarse grade to fine grade, silicon carbide memory sheet. Then after that, we have to etch the specimen. Since it is a ferritic steel, we have used Willard's reagent as a etchant. That's a Willard's reagent. Then after etching, this is a photograph. You can see in the case of 200 rpm and 500 rpm, irrespective of the rotational speed, complete penetration was achieved. But another information, the morphology is getting changing with respect to the rotational speed. Here you can see the onion ring pattern of material flow is noticed, but on the case of 500 rpm, that kind of morphology is not there. And this is the typical metallurgy of the friction stir weldment. This is the stir zone, thermomechanical affected zone, then heat affected zone, then base material. So here the heat affected size we have measured with respect to different RPM. In the case of 200 RPM, the heat affected size is 1.25 mm. Okay, this is my unit is micro mm. In the case of 500 RPM, it is 1.9. With respect to increasing the rotational speed, the heat affected size also getting increased, because the rotational speed will decide the thermal cycle. Since high thermal cycle will give the higher width, that is why it is increasing. On the other hand, In the case of P9 side, since it is a dissimilar weld matrix, the P9 side heat affected zone size is less in compared to the P22 side, because P22 side, P22 is, that means 2.25 chromium molybdenum steel, the thermal conductivity is 33 watt per meter Kelvin. But in the case of P9 steel, the thermal conductivity is 19 watt per meter Kelvin. Since there is a significant difference in the thermal conductivity, that heat flow is also disturbed. That is why the 2/4 1 mole side, the heat affected zone size is increasing. That one we have noticed. In addition to that one, with increasing RPM, heat affected sites also getting increasing because of the different thermal cycle experienced with respect to RPM. So this is a photograph of Sirjon. This is a gate tick welding photograph. You can see the welded profile. This much is the heat affected zone. The heat affected zone size is, you can see it is 2.8. In the case of friction stir welding, the heat affected size was 1.3 mm only. Again, comparing with the 9 chrome steel to 2/4 1 mole steel, there is a significant difference in the heat affected zone size. In the case of 9 chrome 1 mole, heat affected zone size is only 2.8 mm. But in the case of 2.25, heat affected zone size is 3.2 mm. So here, then we have noticed that there is a evolution of martensitic phase. You can see this is a lath martensite. This is the martensite is very hard. So in order to make it for engineering application, we need post-weld heat treatment. What is post-weld heat treatment? After welding over, we have to take the weld joint to the predetermined temperature and hold it for a particular time. Then we can slowly we have to cool. So this is called like this is called post-weld heat treatment. So we have taken the sample for the post-weld heat treatment. This is a PWT cycle. This is a heating, then hold it for 1 hour, then cooling. Since this plate thickness is only 3 mm, we kept it for only 1 hour duration. So depending upon the thickness of the plate, we can change the timing. And the temperature is, we have taken the temperature of 750 degrees Celsius, because the heat treatment temperature should be below that of AC1 temperature. AC1 nothing but austenite start temperature. So since the austenite start temperature is roughly 780 degrees Celsius, so we are keeping for the 750 degrees Celsius for 1 hour duration. So after doing, there's a significant changes we have noticed. The same cross-sectional photograph you can see, there is a evolution of soft color, white color and red color contrast. So what is this? So we are more keen to understand what is there. So soft zone, nothing but different kind of grain orientations are there, morphology changing is there. To study that kind of soft and hard zone, one line scan we have taken. That line scan is done by the SEM equipped EDS analysis. You can see there is a mapping of chromium. There is a diffusion of chromium in the material, because one side there is a 9 chromium, another side is 2.25 chromium style. Since there is a changes in the carbon, there is a diffusion of chromium we have noticed. Because of that chromium diffusion, this kind of white color layer, hard color, the black color layer we have noticed. Wherever the white color region is there, that region is carbon depleted region. Wherever that black color layer is there, that color is carbon enriched region. That one is applicable for the even with the ATIC welding process. So then coming to the hardness profile, we have measured the hardness across the weld material from this end 9 gram side to 2/4 1 mile side. This is the, you can written here, this is 9 gram side. This side is called 2/4 1 mile side. Base material is almost steady profile. Once it is touches the weld joint, then hardness is slowly increasing. The hardness is roughly, you can say, this is the black color and red color. You can see the hardness is very high. You can see it is 480 VHN. Why this kind of steep increase in the hardness? Because of the evolution of the lath martensite morphology. Irrespective of the rotational speed, both 200 as well as 500 RPM, both showing the higher hardness. But by doing the heat treatment, that post-weld heat treatment, the hardness is coming well down. You can see this pink color and blue color is coming down. Earlier, in the as welded condition, the hardness was very high, 450 VHN. But after doing the post-weld heat treatment, hardness is drastically reduced to it is 280. because this a tempering happened because of the tempering treatment, because of the post-world heat treatment. Lathe martensite is changed to tempered martensite. So tempered martensite means there is evolution of precipitates. So that's why hardness is coming down. So, and other interesting thing we noticed, there is a sudden drop in the hardness profile. You can see it's approximately 120 VHN happened. Why this kind of sudden drop is coming? Because we have seen here, wherever it is touching the, wherever it is touching the white color region or dark color region, there only this abrupt changes in the hardness profile we have seen because of the evolution of soft zone and hard zone. You can see here this profile is particularly for the friction stir weldment. Sudden up and down is there. Actually, high hardened lathe martensite is not good for engineering application because it's very hard. Ductility you cannot expect. So we, as engineering application, we need ductile materials. We should have some minimum ductility. Then only we can fabricate the compound out of it. That is why in the lathe martensite one, we have to change somehow. We have to change. So by changing, we have taken the heat treatment. But heat treatment, what happened? Because of the change difference in the chromium content, there is a interdiffusion happen. There is a soft zone and hard zone happening. Because of the soft zone and the hard zone happening, this kind of sudden abrupt changes in the hardness profile we can notice up and down. This is not favorable for the engineering application. So this is the hardness measurement from the top to bottom. Top to bottom we have taken. This is the measurement from the top to bottom we have taken. From there, you can see the stir phase showing the hardness of 470 VHN. Roughly, you can see 470. But the stir root, almost steady hardness profile we can receive in the case of as-welded condition. As-welded means without doing heat treatment. After welding over, we have measured the hardness. So, in the as-welded one, steady hardness profile is reached, and also it means that uniform temperature across the weldment is noticed. Okay. After doing the post-weld heat treatment, as I explained, wherever the soft zone and hard zone was there, the sudden abrupt, this kind of uphill and downhill profile of hardness you can see. Okay. The same things are applicable for the ATIC welding also. You see in the ATIC welding, after the welding over the black color layer, as welded condition, initially it was base metal hardness was around 180 VHN for the 2/4 side. For the 9 chrome side, hardness was roughly 200 VHN. After doing the welding, the weld material showing the higher hardness, roughly you can say 430 VHN because of the lathe morphology. But after doing the post-weld heat treatment, the hardness is coming down to the profile of 250. But only the abrupt changes happening on the fusion line, because there only the border line between the high chrome side and the low chrome side. That's why this kind of changes happening. In the case of ATIC welding, steady hardness profile. In the case of as welding, after post-weld heat treatment, hardness is coming down because of the tempering action. So now, coming to the tensile specimen, we have fabricated the flat tensile out of it, and we have to study where the failure mode is there, what is the yield strength of the material, what is the ultimate strength of the material. You can see in the friction stir welding, irrespective of the rotational speed, both the specimen has failed in the exactly at the weld center only, because there we have seen soft zone and hard zone formation. Because of that, failure was in the center. In the case of ATIC welding, activated TIC welding process, the failure was in somewhere near. But in order to study the exact failure location, we have taken out the sample from this region, we have polished it, and we have done the etching with the Villard reagent. From the etching contrast, we will come to know that where the exact failure. You can see this is the weldment photograph, welding photo, weldment. This is a heat affected zone, but the failure was in the base material only. Another interesting thing we can notice, the failure mode is cup and cone mode of fracture. Cup and cone mode fracture is typical ductile mode of failure. If it is in a brittle mode of failure, means the failure plane is exactly 90 degree. That in the initial cases, from the diffusion bonding of titanium to 304L stainless steel. In that dissimilar matrix, we have seen failure was in exactly perpendicular to 90 degree. That failure plane is 90 degree. But in the case of ductile mode of failure, the failure plane will be 45 degree. Okay, this is a called cup and cone fracture mode. Okay. So here already we have seen, because of the evolution of soft zone and hard zone, the failure was in center of the world. So here you can see this is a tensile properties. The base material of 2/4 1 milli, that is called 2 P22. 2/4 1 milli steel is base material, ultimate strength is 551. In the case of P9 means 9 chrome steel. This P9 steel is ultimate strength is 642. But in the case of friction stir weldment, the it is reaches 521 and 530. But in the case of ATIC welding, it is 553. It implies that even the friction stir welding, we can achieve 95% of the strength of the material than that of ATIC welding. Because another important information is, in the case of ATIC welding, HAZ thickness was wider. It is roughly 2.8 mm. But in the case of friction stir welding, since it is a solid state welding process, HAZ thickness was very less, 1.35 mm only. Why we are more keen to know about HAZ thickness? Because heat affected zone was the one of the weakest zone in the weld material. Especially this kind of ferritic steel material, 9 chrome 2/4 1 milli steel, there is a failure called type 4 cracking. That cracking is occurring in the heat affected zone only. So one of the problem to mitigate the type 4 cracking, if you are avoiding the heat affected zone, then the possibility of reducing the type 4 cracking. So one of the possibility of type 4 cracking is we can control the thermal cycle. So that controlling thermal cycle is possible in the case of solid state welding process like friction stir welding. It is possible, and we have noticed we can nearly 50% of the width we can minimize. Only thing is little bit problem in the ultimate strength of the material. That one we can able to manage by changing the rotational speed. Now again, this is giving the idea that still there is a scope to avoid the soft zone and hard zone. Soft zone and hard zone is cannot be avoided if you are doing post weld heat treatment. Why post weld heat treatment? Even since there is a lath martensite was there, that martensite evolution we can be avoided by controlling the thermal cycle. That one is possible by changing the parameters. That parameter is feasible. We can, if you have done the friction stir welding lesser than 200 rpm, there is a feasibility to change to stop the or to bypass the evolution of martensite. If you are bypassing, if you are controlling the evolution of martensite, then there is no need of post weld heat treatment. If there is no need of post weld heat treatment, then there is no question of soft zone and hard zone formation. If there is no question of soft zone and hard zone formation, then there is no brittle mode of failure you can expect. Okay, that way it is possible in that way. So here another small study we have done, that is a composite fabrication from the waste material to product. Same processing we have done with the polymer one. This is a composite developed, and here we have taken the XRD and all thermal study we have taken, and significantly we have found out one composite fabrication also possible by these friction stir processing. This is all about the material characterization. So we have seen from the visual examination, then from the microscopy like optical microscopy, scanning electron microscopy, the application of the X-ray diffraction, the application of energy dispersive spectroscopy EDS, then application of the microstructure characterization, then mechanical property evolution by the hardness measurement or tensile testing, and the mode of failure. Again, the failure analysis topography study by the SEM. This all we have seen. Now, we can understand this all the characterization techniques are involving, then only it's possible to a material scientist to design the material. It is a backbone of the materials laboratory. Okay, do you have any question? Please feel free to ask. Yes. Yeah. Yes. Actually, while doing the post-weld heat treatment, then only that kind of diffusion phenomena happening, because diffusion is a thermally activated process. While heating, it start moving. Then what basis it is start moving? Because of the difference in the chromium concentration. Since there is a chromium, there is a huge difference in the chromium concentration. One side 9 chromium is there, another one side 2.25 chromium is there. Because of the difference in the chromium, that interdiffusion will taking. Carbon will start moving from one location to another location. That is why that kind of soft zone and hard zone forming was noticed.
Okay, sir. Then why we can control by this PWHT controlling?
Yeah, we can control.
Okay.
Why we have done the PWHT? Because of the lath morphology of martensite was evolved. Why we are very fear on that lath morphology of martensite? Martensite is the hardest phase, but it is a brittle one.
Yes.
For engineering application, we need ductile microstructure. So to changing the martensite to tempered martensite, we have taken the post-welding heat treatment. So if you would have been control that martensite evolution in the weldment, then there is no need of PWHT. But is it not possible to control the lathe morphology of martensite in the case of fusion welding? Because its material itself, it's a ferritic steel, so carbon equivalent is according that martensite will come, because it's a high alloy steel. Okay, so one chance is there in the case of in solid state welding technique. We can by there we thermal cycle is in our hand. We can change the thermal cycle by choosing different material processing parameters. So there, if you do the changing the parameters, then we can minimize the thermal cycle. If you minimize the thermal cycle, then martensitic formation you can minimize. So in that way, then post welding heat treatment you can avoid. If you are avoiding, then soft zone, hard zone formation you can mitigate, then properties will be enhancing. So this is the processing route. Now it is very clear from the processing how the performance coming. Okay.
Okay. Okay. Thank you, sir.
Okay. Any more questions? Okay. So here again you can see, in addition to the subject, the same thing is clear. See here, always whenever you are doing some project, this one you should always in your mind actually, like processing techniques. So now you see, by doing the fusion welding is one of the processing. Now where we end up? We end up with the brittle mode of failure, ultimate tensile strength was less, ductility elongation percentage was less. Okay, but in the if you do the friction stir welding, by doing the severe plastic deformation, we have changed everything. We changed the microstructure, and other thing, there's no need of shielding gas also, correct? But in the case of fusion welding, we need a shielding gas. Okay, again for shielding gas you are putting, you need to think which shielding gas you need to go, whether you need to go for argon or you need to helium. These two are big differences there. Even though both are coming under the noble gases, argon ionization potential is 15.6 electron volt, but in the case of helium 22.5. Then why we are more interested in the ionization potential? If it is in higher ionization potential, lesser heat input is sufficient. Okay, why we are more keen to heat input? Because heat input is the one parameter, that is the only one thing deciding, one of the parameter deciding the heat affected zone size. In all the weldmen, the weakest region is heat affected zone only. The definition of the heat affected zone, you can say the portion of the material adjacent to the welding region is affected by welding heat. One is maybe from the thermal cycle, that is nothing but heat input deciding. Second thing is the material thickness. If thinner material, if material heat conduction will be very fast. If it is thicker material, it will be minimum. So these are all the parameters. In that, out of that, the heat input is a controlling one. Okay. So for the heat input, for making the minimum heat input, what we can go? We can, if you go for the higher ionization potential shielding gas, then we can minimize the heat input. Minimum heat input means minimum lesser narrow heat affected zone will come. Narrow heat affected zone means the chance of failure, that possibility you are neglecting actually, possibility. That's why the high end welding process is always preferable. High end in the sense like electron beam welding, laser beam welding. The problem with the laser beam welding, electron beam welding is costly. It's a very production of electron beam welding, again vacuum chamber, is all cost. It's a cheaper one. Always you go for the cheap and best. That is why performance per cost ratio. As a design engineer, our thinking should be always performance per cost ratio. In that aspect, fusion welding is best. That too, conventional fusion welding is best. In that, which one is again best? Just in that, thick welding will come. Thick welding will produce the high purity welding process. In the thick welding, that ATIC welding come into the picture. That ATIC welding is nothing but activated thick welding process. There, what will do before starting the welding process, there one in-house fabricated one flux they will put. The flux what will do initially, if without flux, if you do the welding, the heat conduction will be this way. It will go. But if you apply the heat, the conduction will be this way. That means reversal of Marangonic convection. That phenomena is called reversal of Marangonic convection, because this whatever the flux element you are coating, because of the surface tension of that one, it is getting flow is ulta this way. If it isn't going in reverse, then depth of penetration will go high. If it isn't going this way, HAZ zone will come bigger. If it isn't going this way, only depth of penetration will be higher, but narrow heat of it will come. That is why the activated thick welding is tremendously people are using. Even 10 mm thickness also, without preparing the V groove, directly we can do the welding by the ATIC welding. It's possible. Only thing you need to choose the current and voltage and welding speed accordingly is possible. Otherwise, 10 mm thickness, one spot welding, people are searching for the EB welding only, electron beam welding only. But in the advancement in the thick welding, that is with the help of ATIC welding, without preparing the groove, the autogeneous itself, we can do the welding. Okay, that way it is manageable.
Sir, in one of your PPT,
Mm.
I see that onion ring pattern.
Onion ring
Onion
pattern.
ring
Yes,
pattern
yes.
is the main pattern for FSW.
Yes, it is expected, and also that pattern, that onion ring pattern is evolving because of the dynamic recrystallization. Dynamic recrystallization, how it is happening? Because of the stirring action of rotational tool, that severe plastic deformation happening. That's why the new strain-free grains are coming. That onion ring pattern is applicable only with the lowest stacking fault energy material. Like aluminum, if you do well, definitely you can see that kind of onion ring pattern.
Okay, with
Okay.
changing the material, the pattern also be changing.
Changing.
Okay,
That
okay,
too
okay.
again with respect to RPM is playing. You
Okay,
see, in our case, in the case of 200 RPM, we noticed that onion ring pattern. But on the case of 500 RPM, that kind of onion ring pattern was not there. So again,
RPM also.
yes, it's playing a role.
Okay, okay,
Yes.
sir. Thank you, sir. Thank you for the information.
Okay.
Thank you, sir.
Okay, sir. With this, we'll close this section. Okay, thank you. Thank you all.